Alo.
Alo.
Rồi. Okay. Very nice. Cái này chị dùng bản web đúng không? Ủa chị nghe em không?
Oh sorry chị Miu. Em nghe chị không?
Có, em nghe chị. Nó hơi bị kiểu echo.
Alo.
Em nghe chị.
Okay, okay. Hello.
Hi, hello.
Hi, can you guys hear me clearly?
Yeah, super clear.
Okay. One
Perfect.
second, let me turn on the. Okay. Cool. Hello, everyone. So I would like to start the meetup today. If you cannot hear me, let me know. Okay. Okay, so for the first 10 minutes, we will do a quick introductions about the meetup, and we have some folks here, so we can have a quick intro about everyone to get to know each other. So welcome to the online meetup to discuss paper and data science. When we provide the space, we hope that we can encourage you guys to read more papers and read in a fun way, because we know that paper is gonna be boring. But if we read within a community, our friends and peers, so we can like exchange our thoughts and motivate to read more paper. So the topic today is distilling knowledge in a neural network. Our facilitator is Patrick Trung Phát Uyển. So I will let him introduce himself later. For some notice about the meetup, I have left the link and direct message to each of you about the link that you can use to say we can do follow up later after the meetup for further discussions, or if you are late for the meetup, or if you miss the meetup, you can come on the these links to to watch the recap video. Okay, so long story short, I think we should dive in the introduction. My name is Daphne, and I'm the community manager of HashRain or FlowNode.ai. So we run these activities at a nonprofit activities to help communities to connect and exchange thoughts on paper. So I would like to introduce the next person to introduce, maybe Patrick.
Yeah. Hi guys, sorry for my camera. It's gonna. My name is Patrick. I currently CS undergrad in Vietnam. So I'm interested in the field computer vision, machine learning, and deep learning. So today I'll be the facilitator for today's topic, distilling the knowledge in neural networks. I hope you guys would like it.
Great. Patrick, can you point the next person to introduce himself, him or herself? Yes.
Yeah. So I have a friend here. His name is Phúc Hiếu, but I don't know if you want to talk. Hiếu, are you there?
I saw Fuku on the line.
He said that he have a cough, so he won't want to talk.
Maybe give a short line introduction. Hello, everyone. Okay. Okay.
Jack Simon. Jack Simon is also my friend. Hello, Jack. Are you there? Looks like his mic is not connected.
Okay. Maybe the next person first, and then we go back to Fuku and Jack Simon.
Well, I can start. That's fine.
Okay.
Hi guys, I'm Kai. I'm the founder of HashBrain. So like what Daphne said, the focus of the group is on community sharing. I'm currently interested in anything text-based, extracting intention from text better, searching recommendation, and encoder-decoder networks with attention on text. Yeah, that's a brief intro.
Okay, cool. I guess Lewis, maybe you wanna introduce about yourself. Hi, Lewis. Are you there?
Oh, we got new friends, Mawson.
There's Lewis and
Nice to meet you.
oh, Mawson.
Can we get to know you, Mawson?
Oh, Mawson came to a lot of the events. Mawson, your mic is on mute. You want to do a quick introduction?
About what?
Yourself.
Yourself.
It's a two-liner. Yeah.
I just came here. I don't know what is the topic.
Yeah. We were talking about we just started and we're doing a quick three-liner introduction by yourself.
So I'm Mosen, and I'm interested in machine learning. And hello,
Paul, where you from?
I'm from Iran.
Ah, cool. I think we know each other, but then the rest
Yeah.
of yes. So just a short line introduction.
Yeah.
Anyone haven't got a chance to introduce? I think iPad DR. Are you there? Okay. It seems that you're not there. So Hoàng Phạm, would you like to give a short introduction by yourself?
So you guys can join the mic by pressing the button at the corner left.
Hoàng Phạm, are you there? Okay, so if you want to introduce yourself, feel free to drop a line about you in case that you don't want to raise voice. Okay, so we have 3 minutes left for the introduction.
I think that's fine. I think we can start.
Okay,
The rest, we should just chat them. I don't know if they're online. Yeah.
Milk mic. Ôi, Hoàn, do you want to introduce yourself?
Me? Hello?
Hi, Hoàn.
Hello? Yeah, hello
Hi.
everybody.
So maybe give a quick background about yourself, your name, what are you doing, why are you joining the discussion today, what you're looking for, like, yeah, just for everyone to know, and maybe we can do the networking after the meetup.
Okay. My name is Hoàng, of course. I graduate computer science at the Hanoi University of Technology, and currently I'm working at Ho Chi Minh City as a junior software developer. Yeah, I actually I once registered for a course from Hasbrain, but I did not have time to join, and yeah, yesterday I saw this meetup and just yeah register to join, and just I am very new to the AI, everything, just curious about AI. Yeah,
Okay.
so yeah, thank you.
Cool. Sounds good. So I saw some two new friends coming. Hồ Sĩ Tuyền, do you wanna give a quick introduction about yourself?
Hồ Sĩ Tuyến is actually
Sĩ Tuyền. Yes,
Tuyến.
your friend.
Can you let any others to know you? Hello, Tuyến.
Hello.
Hello. Can you introduce about yourself?
My name is Hồ Sĩ Tuyến. I'm a student. I just go to see about the topic.
Okay, cool. Okay, I think the last friend would be Manmit.
Oh,
Hi, Manmit, are you there? Okay, you guys can choose to either turn on a micro and raise voice, or just feel free to leave a message about yourself if you would like to. Okay, so let's dive in the discussion now. I will leave the stage for Patrick. Okay, so I shall stop share screen.
Ooh. All right. So you guys see my screen? Can you guys see my monitor?
Yep.
Yes.
All right, let's see. Let's move this.
Hey, Daphne, can you repost the link of the paper on the chat?
This okay.
So the name of the paper is actually Distilling Knowledge in the Neural Network, with the same title as our topic today. My name is Patrick Nguyen. I'll be your facilitator for today's topic. So I think this topic is quite interesting because when I talk to my friends about this topic, and he say like that, it's not gonna work, but it's actually work, and I'll tell you why. This technique gonna work and can improve your neural networks performance. So this is the picture of the paper. You can search it up on Google. Distilling the knowledge in the neural network. So the paper is written by Hinton and his friends. It is a quite popular paper during 2015, and there are some follow-up papers that also the upgrade of knowledge distillation in 2019. It's still in the development. Okay, so the main idea of knowledge distillation is how you can distill or condense a teacher model, which is a really big model, into the student model. This is quite similar to what we think in our life, right? Because if the student learn alone, they cannot learn a lot of things, and they cannot learn things like more generalized. If the student have the teacher to guide them, then the student can learn faster and even more more performance with greater performance. Okay, so because for the time being, we've been developing a lot of great and powerful neural networks, and even very complex one. In Kaggle, we try to build a really big like ensemble models that consist of like 4 or 5 networks. So the network gets bigger, along with accuracy become greater. Um, the needs of reduce these network into atoms, that you can then deploy into production. That's the main goal of the paper. So before I talking what is knowledge distillation, I'm gonna show you the result that I got after applying this technique. So for the teacher architecture, the teacher that guide the students, I use the simple CNN. So this is quite a simple experiment that I made. So the CNN is it consists of like convolution layers followed by pooling layers, end up with 256 units then layer, and at the end there's a softmax. So you can see there a convolution pooling, and a flatten connecting with 256 unit lengths there. This architecture is about consists about 1 million parameters, and I use another student architecture, which is a really small one. From the picture 28 times 28 times 3, I flatten the picture into a vector, and then connect it in with the 64 dense layer, and at the end the softmax. So this architecture consists of like 100K parameters. So this is the result. So for the teacher model, I trained with the CNN. This is 70.75% with 1 million parameters. But if you see when the model is trained alone, it's only got like less than 40%. But when it's trained with teacher, it's almost 50%. Okay. So what is the history of knowledge distillation? So knowledge distillation is been there for a very long time. So in 2006, Gu and Silu and his friend um, proposed the idea of knowledge distillation. I cannot find this paper. I hope anyone could find it. And then in 2014, Van Kurana proposed a loss function on how you can train the knowledge distillation. At then, the knowledge distillation wasn't popular enough, so Hinton tried that this idea of knowledge distillation is quite interesting, and he wanted to do a review on that, and he published a paper on knowledge distillation in 2015, and this become viral, so much viral. Both you in the academia and industry to reduce the size of the neural networks. And let's get straight into it. Okay, so before I'm asking this question, so why I'm asking this question? Why hard labels are bad? So why does it have to do with the knowledge distillation? So in this sharing, I want this topic to be top down as possible. So from now you can forget everything I'm telling you about the knowledge distillation parts and just go with the flow, right? So our first claim is that hard labels are so bad. So I'm gonna explain why is it and what does it have to do with the knowledge distillation part. Okay, so you know that when you train neural networks, you have to encode categorical data into the something called the one-hot encoder. That's like the matrix of ones followed by a bunch of zeros, like 1, 0, 0, etc. So why this is so bad? This is actually the things that we do, but we don't realize it's not that bad, but it prevents the neural network to be perfect. So I want to explain to you how backpropagation works when you learn and you try to train a neural network. So I use this really simple neural network here, which consists of no layers. The input of the network is like features like paws, body, bark, nail, and wheels. These features corresponding to dog, cat, and truck. So you know that paws, body, male corresponding to cat, body part corresponding to dog, and wheels corresponding to truck. So you can see that body, both the dog and the cat has body, right? And the truck is alone have the wheels. So imagine you put this picture of the truck into the what would it do? So you can think the first layer of us is like a feature extractor. So when you put the truck inside the neural networks, it actually activate the nodes that exist the wheels, right? So we feed forward this, and at the end of the neural network, we will do something called the we calculate the loss function, right, via a cross entropy. That's we already use for the training part for every categorical classifier, right? So when we after we the main goal of this cross entropy loss is trying to match the distribution of the last softmax layer to the true distribution of its label. So it actually means with input of the truck, the network should be one at the node of the softmax of the truck, right? And I want to minimize dog and the cat probability to zeros. I want to reduce cat and dog to atoms, right? So after that, after calculating the dog, they do something called the backpropagation. It means that these weights are gonna adapt to make that happen, to make if the truck input into network, the truck has to come out of network in softmax. Right? So what the network trying to do is trying to maximize these weights. So every single input of the wheels will affects the softmax node of the truck, and minimize the wheels corresponding to the dog and the cat. So why? Because if the wheels is highly activated, this shouldn't affect the node of the dog or cat. Should be the dog and the cat shouldn't be highly activated. Okay. So what happened if this is a dog? So if this is a dog, the body and bark will be highly activated, right? Because their body and the bark feature in the picture. So the network will try to maximize the softmax nodes of the dog and minimize the others. The network after backpropagation, they're gonna minimize these way with the body and bark correspond to the dog, and minimize body to the cat and body to the truck, and bark to the cat and truck. So do you guys see something wrong with the picture? See something wrong with the picture? Hello?
Yeah, maybe the cat, because there are some overlaps.
Yeah, the cat is actually overlap with the dog for the body parts, because you see this part, because the cat also have the body, but you minimize it. You minimize the chance of input the body and output the cat. So this is the really bad thing about the hard label alongside with the cross entropy, because the cross entropy trying to match the distribution of the true distribution, which is 100, to the softmax unit is 100. So for every dog's image, we try to maximize the body corresponding to dog, while minimize the body corresponding to cat. And for the cat isn't happy with that. So the cat gonna take that. So its body is his, right? So he's maximize the body and minimize to the dog. So the dog again take it. Though it's mine, you idiot. I'm gonna take my body back. Then this go it's go forever. Okay, so I call these things is like a noise in labeling dataset. So there are a bunch of noises in dataset that you can file, like the picture of a woman holding dog, but label is a dog. The label doesn't show like how many percentage of it being human or being a dog, but only label 1 for the dog and 0s for others. That's just the really bad thing. Or the dog look like the cat, but the labels is 100, which is not the things we want. And also this type airplane also look a bit like the helicopter, but the hard label doesn't show that, right? So because we're using a neural network, we try to approximate a map function called the f functions, that mapping from x to y. So the y, which is our prediction the y, which is our ground truth, should reflect accurately what is appear in x, which is the picture. Right? You guys get that?
Yep.
Okay. So any ideas on how you can solve the problem? Let's discuss the idea.
More layers.
How do you have any ideas to solve the problem?
I think isn't having more layers in between going to solve that problem, because essentially, I don't know whether in the previous diagram you show it's just assuming 2 layers, right? So if
Yeah.
it's directly trained, then obviously you cannot, when you increase the probability that the body belongs to the dog only, then you are essentially decreasing the fact that the body belongs to the cat. But having more layers means that they can achieve both, because it's a combination of body and bark that makes a dog, right?
Yeah, that's really sense. Like we only have 5 notes, so that the dog and the cat have to share the body. But if we have
Yeah.
like 6 notes, we can have the dog body and the cat body. Don't have to share, right?
Well, I'm not thinking about having more nodes. I'm thinking about having more layers in between the two input and output.
Yeah.
Because it's going to learn representation that, the combination of the paws and the body and the meow makes the cat, right? It's the
Yeah, right.
combination that matters.
Yeah, because I think that the bigger neural network can prevent these noise to be vulnerable.
Yeah, correct. It's having more layers.
But if you have like a really small one, the effects of these noise will be really tragic.
Bigger.
As you can see in the picture. Yeah. So the one solution is to adding more layers, and I had another solution is adding more nodes in the same layer. So another solution is that you can use the softened labels. For this picture, the dog is 0.90, 91%, but there are a small fraction of it's in the cat. So this type label is gonna show the similarity between each class. So the dog is kind of similar to a cat, but far less similar to a dog. So this actually happened in the back end of the neural network. So trying to maximize the body corresponding to the cat, but hey, the body you can share with the cat. You don't have to the dog take the body and the cat take the body, right? So the question is that where can we get these softened labels? Yeah, are we gonna relabel everything and it costs a lot of money because of a lot of like human power? Yeah, actually I've already done that. Solved the question. So there's a finding that when you divide the logits, which is the numbers before you apply the last node of the neural network before you apply the softmax function. It's the logits. So you divide it by the number called the t. We call it the temperature. So the logits become close and closer together, and the probability will come closer and closer together. So I'm gonna do a demonstration. So let's say we put in the dog, and the logits for the dog is 7, the cat is -1, the truck is -39. So as a regular way, you're gonna apply softmax, and you get a really high probability dog, 0.99. The cat is somewhere around 2.47 e to the -3. And it is far less similar to a truck. The dog is far similar to the truck, right? And you want to amplify this probability. You're gonna divide it to a number called the temperature before you apply the softmax, and the logits become smaller, much smaller, and comes close together. And when you apply softmax, probably it shows up like this. The dog is 76%, the cat is 24%. So we call this thing is the dark knowledge. The dark knowledge is something you can generate by a really big neural networks, and you can then use that knowledge to train a really small one without hurting their performance. Without having. Yeah.
Sorry, can I ask questions now, or should I leave it to the end?
Yeah, you can ask it now.
Okay, I have a question. So actually 2 questions. The first one is that soft labels means that essentially it's not binary, right?
Binary.
But that doesn't softmax already do that in the sense that it gives you a probability density. So everything adds to 1, right?
Yeah.
So doesn't it already do that?
What? I didn't get that.
So it's not. I mean, the idea, the mathematical like equation of softmax is that it tries to calculate the probability density first, right?
Yeah.
And then takes the maximum probability, and then that outputs as 1, correct? The rest are 0.
No, not actually. Not actually. The softmax, not trying to. No.
I mean, it outputs a probability density, and everything adds to 1, basically. So typically, we do classification. We will take the top.
Yeah. Like the softmax
So
trying to bias toward each class and give so much probability for a class. You know, when you do the cross entropy loss optimizations, it's actually match the distribution of the softmax to the crowd truth, which is absolutely the network absolutely wants the output to be 100.
yeah, correct. But in the case that the cats and dog, the dog and cat being very similar, then it's gonna have a very middle state probability.
Yeah.
Right. So isn't that kind of like a soft label? You understand my question?
No.
Okay, so let's say in following your previous example, let's say I give an input that this thing has I'm the only input is like that the entity has a body.
Yeah.
Right.
Yeah,
Then the neural net is likely gonna say, okay, that's like similar probability between the dog and the cat.
Yeah.
Right. So
Okay.
you understand the question? So like in sense, the softmax is kind of outputting a probability that is soft. It's not telling you that it's definitely a dog.
Yeah.
It's not like a hard label.
Yeah. Because in the end, you only try to. So when the softmax, you got the softmax and you try to take the Rmax to see what class is it.
Yeah. So that's my point. Like if you remove the final step up, which is just take the highest probability, right?
Yeah.
It's output the step before that, then isn't it the same?
What the logics? The logic? You mean the logics?
Yeah, correct. I mean, you are essentially calculating the probability. Everything adds up to 1, right, after the outputs.
Yeah.
And the fact that if I put in the body, and then the output of the dog and the cat is going to be very similar because there's not enough information to tell whether it's really a cat or a dog, right?
Yeah, right.
So the output is going to be like maybe 0. I'm going to make out a number like 0.4 something, and then the other one is 0.4 something.
Yeah.
And that's kind of like a soft label, no? So like my first question is like, isn't that very if you don't take the max part, which is just take the highest probability and output that as a class, you just remove that. So wouldn't that be already a soft label?
Oh, that's actually the thing that we're trying to deliver in this part. So we're trying to use the really big neural networks to generate those labels and put those labels to train our student models. That's what we do. But
okay, but I guess my question is your point about soft and hard label is that hard labels are bad, right? Because they are like they force the network of small networks, right, into certain states.
Hi, can I just ask, is it because with this dark knowledge, the probability of dog and cat is closer, and then the probability of cat is much more different from the probability of is that what you're trying to achieve versus the direct softmax probability output?
Yeah, that's right.
So Kai, to your earlier point, I think the softmax output, the probability does have soft label, but then if you look at the probability of 2.46 times e to the power of -3 and then 1 times e to the power of -20, those two are both very, very small versus the dark knowledge output is 0.76, 0.24. So both seems to have a reasonable probability versus the track, which is almost impossible. So I think that's what we're trying to achieve with soft label, right?
So, which brings me to my second question, right? Then firstly, how do you pick a temperature? Do you just pick the highest number?
So in the paper, Hinton tried a really small neural networks, and he find out when you use over 300 units, 300 units per layers. So you want to pick the temperature between 5 to 8. And when you strictly reduce the numbers of units in the layers to 50 units, between 2 and 3.5 works really superior.
So it's like there's no actual formula. It's just like a sensing kind of thing.
Yes, there's some implementation on this, and in the industry they use the temperature of 10.
10.
Is this
like the default one? 10.
Is this one of the hyperparameters that people typically optimize, or people just typically pick 5 to 7 or 2 to 3 depending on the network size, as you mentioned?
Yeah. So in the industry they use the temperature 10. This is like a hyperparameter that we choose. But over 10, 10 and over, it's gonna use a similar results.
Okay, I don't know whether you have more like slides to talk about that after this, but then I feel like the step to divide by temperature is somewhat like a normalization step. So what's the difference between this and normalization?
It's not normalization is actually a linear transformation, but you only you apply the temperature before you apply the softmax, which is the non-linear transformation.
What do you mean by normalization? Isn't normalization usually applied on feature engineering?
Yeah, but this is okay. So isn't this what we're doing? We apply like a linear transformation on the input.
No,
right?
But it's before you apply the softmax. Then it's not a linear transformation. Before it's before you apply the softmax. So you see when you're not applying the temperature, gonna be 0.99, but you apply the temperature into the logits, not you apply the temperature into the softmax. To the logits before it. And the softmax is the nonlinear operation. It's different.
Okay, interesting. Because I think I may be wrong, but I think I've seen several like bigger nets, like mobile nets, right? They apply normalization in between.
Yeah.
I mean, it's definitely in between like the bigger nets. It's not like after softmax or something. So softmax is a final layer, right?
Yeah.
But
this is also not in between layers, right? This is after you finish all the layers and before softmax.
I didn't catch that.
Her question is that for logits, like the first table, is that the layer just before the final layer, or is that the input layer?
Just before the final layer. This is the formula divided by T. The Zi is actually the logits.
And is that the layer before the final layer?
Yeah, before you apply the software activation.
Just before, so that's the final layer.
Yeah.
The layer before the final layer.
Yeah. So it's a nonlinear transformation, actually.
Interesting. Okay, maybe I need to read a bit more on that. Cool. Thanks. Sorry, go on.
It's okay. I like questions. Okay, so I'm gonna do visualizations of the dark knowledge. So this dark knowledge I generated from the CNN, which is the bigger model. So you input the horse. So So the y-axis of the graph represent the probability of the class on the x-axis, corresponding to the temperature. Right. So if you input the horse into the network without the temperature, so there are really high probability of this being a horse. Right? It's over 100%. And if you divide it somewhere 5 to 10, you can see the dark knowledge appear. So it's somewhat similar to deer and somewhat similar to a dog. And the shape of the horse, it kind of looks like a dog, right? But if you use bigger and bigger network, these dark knowledge might disappear. Yeah. So this is the picture of shape.
Excuse me, I have a question.
All right. Okay.
What does it mean temperature 1? Temperatures 50. What is the difference between temperatures?
Oh, so if you use bigger temperature, the lodges will become closer together. Therefore, the probability will become closer together. So if you look at this temperature 1 is actually the normal thing that we do, that we apply a softmax function without any temperature, and we have really probability of this being a force, right? But if you divide this by the t, divide the lodges by t, the lodges become closer together, right? And then the probability come closer.
I understand.
So,
another question, that why you want to make, because you said that when you make it closer to 50, temperature 50, the result is better. But actually I see the temperature 1 give you the best result. Why you want to make the result worse?
No, it's
Call it better.
So I already tell you about the bad thing of hard labels. So when you divide the temperature by its temperature, so it's reveals something called a Doppler lift, can express the similarity between each class, and it won't have. It kind of prevents the thing that I told you that the small neuron will have in the first place. The cat and the dog problem,
Maybe I can try to explain in a different way. So,
yeah.
So basically, the whole idea here is that this picture it may be a horse, but it may be a dog or a deer too.
Yeah.
Right? You can't really tell. Maybe you can tell from the color because you're human.
Correct. Yeah.
But what we will want is to suppress the absolute probability that this is a horse, right? You want to consider the fact that it might be a deer. So let's say, like, if you look at number 10 as a temperature, that gives like a more reasonable output where it is likely a horse, but it may be a deer, right? Whereas 1 is not really good because it looks like it's very confident it's a horse, right?
So why we have to do it? Because when the network say is high probability to is a horse, why we have to less consider a horse?
I'll give you like an intuition on this, and then maybe Patrick can add on to it. So the whole idea of distillation is that you want it to be in a smaller neural net, right? Because we want to put it in a phone, for instance, okay? And just now, the example Patrick gave is that basically there's 2 ways to properly train like data. So imagine you have a lot of data, and in the data, there's a lot of noise in it, right? And then you want to really extract out like nuanced features to know really whether it's a horse or a deer, right? Then you have super huge net, right? Maybe you have like a ResNet 50, which is decently big, and then there are bigger and bigger nets after that. Okay, so for big nets, that's not a problem because like basically you can imagine a very smart person with a very big brain. You give him enough data, he can always pick out the nuance between the data, right? But what if this person is not very smart, right? Then you give him more data, he'll be very confused. And when he's confused, he'll give you a very high probability of something that's wrong.
Correct.
right? So what he's trying to achieve here is that, okay, so if this net is very small, how can we use soft labels instead? Because you don't want to train the net such that the weights are because basically he showed you the example, right, of if the net is not deep enough, then if you increase the probability of it being a dog, you're actually decreasing the probability of it being a cat, although they share similar input features,
Correct.
which is the body. Yeah. Got it? Sorry, Patrick. Yeah.
It's
You have
okay.
anything to add?
Okay.
Yeah.
Really,
I have a question. Yeah. Yeah. So what is the optimum value of the temperature that we use?
You mentioned the industry standard is 10.
by 10. By default, you can use 10, but then you can iterate and use more oddity if you want. But others can really use the same results, as I said.
Okay.
Okay. So the host might be similar to a deer, somewhat similar to the ship, um, somewhat similar to an airplane. Kind of you can fuse it into your in your intuition, and somewhat similar to the automobile, and far less similar to the bird, cat, deer, dog, etc. So this picture is quite interesting. So really high probability of being a truck, but and high and somewhat a ship. But you can see why is it a cat? Why there's no cat in it? So let's mix a guess. This might be the cat ears, right? Uh, we don't know. This might be a cat legs. Yeah, we don't know. So this is the dark language that the bigger network generated for the student to learn. So
Okay.
because as I said, we're trying to learn the mapping x and y, x to y, right? So the y should represent accurately what happened in the x.
Yeah.
Yeah.
Okay.
So if you get bigger neural networks, these cat ears and cat legs might disappear, and the neural network not gonna disguise this as a cat anymore.
Okay.
So this picture is about a cat. It's a cat. That's somewhat similar to a dog, but you can see its shapes, and somewhat similar to an airplane. It's kind of counterintuitive, but who knows, right? So the main idea is to learn from the dark language, what is the software language that contains more information about the class that you want to classify. So the dark knowledge actually show the similarity between each class. So therefore you learn more generic representation of the output file.
So the teacher is trying to teach the student the dark knowledge.
Yeah, right.
So the basic idea is that the teacher is the bigger network here that knows the knowledge and want to reduce the noise in a smaller network.
Yep. Yeah.
Okay.
I have pasted a link on the chat for those who are interested. Maybe later when Patrick finish. Sorry, I didn't know you still have slides.
So I gotta show you a distillation pipeline, so you can later implement for yourself and for your projects, something you work on. Don't be stressed about this graph. I'm gonna work into it. So first, you're gonna put the input X into the teacher model. The teacher model can be a bigger model that you already train on some data sets, and you can use pre-trained models, Coco, ImageNet, something like that. And you apply you remove the last softmax layers and you apply T, and then you light softmax, and recreate these soft layers that you have here.
Sorry, can you repeat that line again? I missed that. So you remove the softmax?
So when you, when you download a pre-trained model, it's actually the whole model, right?
Yeah, correct.
And you remove the the softened layers. Okay, a softmax layer of that.
Okay, so you just take the head basically.
You take the voltage and you divide it by T, and you apply softmax later on.
Oh, okay. So you divide by the temperature and then apply softmax.
Yeah.
You get the soft layers. But this assumes that your pre-trained model is trained on the same labels.
Yeah.
Okay.
So you get the soft labels, and then you're gonna put your X into the student model. Who is haven't ever trained before, and you wanna try to max. You want the soft prediction of that student to match the soft labels of the teacher. So actually, the student has to divide by the temperature, and then apply the softmax, and then you get the soft prediction of the student, the soft prediction, and then you calculate the loss between them. So the soft prediction should match the soft labels. And we use the loss, the KL divergence loss, with the T square as the normalization term. Okay, so we have the first loss. So we continue to input the X into our neural networks and share it. Actually, we optimize the same labels as we do usually. We try to match the hard prediction with the hard label through the cross entropy. Right. There are two losses. There are the noise situation loss, and there are the cross entropy that we already know. Right? Yeah. So we have two loss. So we want to make the ultimate loss. We're gonna combine each together via weighted sum. So we have the student loss and we have the knowledge situation loss. So there's new hyperparameter here. So the lambda represents how much do you want to learn from the teacher. Yeah. The first loss is the KL differential loss. Represent how the soft labels match soft label of the teacher match the soft prediction of the students. And the second loss is the students match how matching of the students to the crowd truth via the cross entropy that we already know. And we do a weighted sum over them. Yeah. And new hyperparameter is lambda. Any question? All right.
Pretty good.
So I actually implement this on my GitHub. You can go at github.com, Patrick Patwin, and you can see I already pinned it here in this installation canvas. Okay, so move on to the next slide. So the pros of the knowledge installation is you can increase the accuracy of the model by via the knowledge generated by the bigger model while maintaining the lightweight for the deployment in your system. Right. And the good thing about knowledge installation is the student model is not prone to overfitting. Yeah, because you try to match the software version, not trying to match, trying so hard to match the hard label. So the student models is not likely to be overfit. There's less computational reply, faster convergence. Because it converts faster because you try to match the matching the soft labels on a wireless power.
Yeah, I have a question. Sorry. Your last point, student model can be trained with unlabeled data.
Yeah.
How is that? Okay, so like going back to your equation again, right? If there is unlabeled data, then that second part of the model don't exist.
Yeah, right. If unlabeled data, you can remove the cross entropy part of the model.
So like if let's say I have 100 labeled data and 10,000 unlabeled data, then do I train it with 100 labeled data together with the 10,000, or do I split it up and train it independently? How does that work?
So this is a graph. I didn't catch that. Okay.
So let's say I have 1,000 labeled data, right?
Yeah.
And I have 10,000 unlabeled ones.
Yeah.
Right. So how do I like implement this? Do I train it together?
Oh, so you can try two phase. The first phase is you're trying to use two of these loss together, but with the unlabeled data, you only have the detailed divergent loss from the student
Right.
group. Right.
Okay, so what you're saying, we train it together and it will update the same weights. Is that correct?
What do you mean by the same weight?
Because we're trying to like train the weights of the student model here, right?
Did you get this?
Okay, so 1,000 unlabeled data, 10,000 unlabeled ones. Do I take 11K as the total training? And just put it in this? So I don't really need to split it up.
If it's one of my case, I'm gonna take on that data and remove all labels and put into the teacher model and generate the labels, and the student will learn alone through the stop labels without the self-learning.
Oh, yeah, which is my question. Why, like, okay, so would that be better than just taking 11K?
You mean that is it better if the student only learn from the teacher, right?
Yeah, because like let's say we set 50-50, right? 50% from the teacher model, 50% from hard labor, right?
Yeah.
And in this case, there's 1,000 labeled and 10,000 unlabeled. And because we set 50-50, then like the other value will be 0, right?
Yeah.
Or just be null.
Yeah, it's like the hyperparameters. So in the paper, Hinton trying to say that when the lambda gets bigger, it's better because you learn mostly from the teacher. But if the teacher model is too small compared to the students, it's like the same size. You should consider the second part of the loss.
Okay, so going back to the question on the labeled and unlabeled data, I think that's something worth thinking about. Maybe have you tried it before, like mixing labeled and unlabeled data?
No, I haven't.
Okay. Because like what you're saying is that if there is labeled and unlabeled data, you throw away the labeled data, or you use the labeled data to train the teacher model more. Is that what you said?
I'm not showing the unlabeled data. I can use the labeled data to generate. So my process is two phases. The first phase is use the labeled data. Then you can have two loss: the self-learning loss and the knowledge circulation loss. And the second, you can use the labeled data for the first loss that the student will learn alone to the teacher. Right? You learn solely from the teacher.
So you have two phases. The first phase is to train with the train label.
Yeah.
So you have two sites, right? And then the second phase is the unlabeled data. Yeah. So my question was that for the second phase of the unlabeled data, do you train it on top of the same weights that you have already trained for the first phase?
I don't know. I haven't tried that, but I can answer that after this minute.
Okay. Yeah, that's interesting. Yeah, I think something worth trying. Because I think in the real world, it's typically mixed. I don't think it's fully unlabeled or fully labeled.
Yeah.
Most of the time. Yeah.
Yeah, because the my lecturer, he said that the word is kind of lean toward the unsupervised learning. Really, and unsupervised learning and lightweight models, and that are two types of the buzzword.
Yeah, but I feel like if we do that, then we are actually overfitting to the trained teacher model, right? Then that really depends on how good the teacher is.
but we already have really good teacher, and we want to the model to be smaller and smaller.
Right. Okay.
We already like in the image recognition task, we already surpassed the 95% accuracy. So why don't we use that knowledge to distill to smaller and use higher?
Yeah. I see what you mean.
Okay. So the bad thing is that we have 2 more hyperparameters to worry about. But by default, you can use the temperature 10 and lambda from 0.5 to 1. And the second bad thing is that the result will be not good if the gap between the teacher and models and student model is big. You know? So actually a study on that. So in the study, they try to use a fixed student architecture and increase the size of the teacher model, and they compare the accuracy. So you can see in the left graph, this is the student accuracy and the teacher accuracy when you increase the teacher size. As you can see, the teacher and the red bar rise because you increase the teacher size. So what happens to the student accuracy is that it's rise from when you increase the teacher size from 4 to 6, but it's going to drop dramatically after reaching the peak at the 6 layer teacher. On the left graph, the students also rise and gonna stuck at the peak, and then gonna drop down dramatically. So there are actually a paper on that. So you wanna do have something called the teacher assistant. It's quite similar to what we think, right? So if the student cannot catch what the teacher said, you can use a teacher assistant to help the student learn better.
Sorry, Patrick. Can you go back because the box is blocking your diagram? Yeah. So what is the difference between the first graph and the second graph? Okay. What's the difference? It looks the same.
It's all the same. It's just another example.
Oh, okay. Okay.
Yeah.
You got it.
So so you're gonna use a teacher assistance. So the step is that you distill the knowledge from the teacher to the teacher assistant, which means the teacher assistant is actually the student of the teacher, right? And then you use the teacher assistant to teach that knowledge to the student. So this graph, this graph this table try out several of paths that you can distillation via a teacher assistant. So this is the first path from the 10 to 8 to 6 to the size to 4 and to 2, you got the accuracy of 14%, right? If you distill a teacher with the size of 10 through the teacher assistant with the size of 8, 6, and 4 to the student with the size of 2, you got the 45% accuracy, which is really high compared to other path, right? So if you use the original distillation I said, is you wanna distill the 10 layers models to the 2-layer students straight away. You get the 42.56% only, but that's still higher than the no distillation model. So yeah. So the key idea is you use knowledge distillation, which is revolves around the soft labels to train the student models. And the second thing is that you can use more teacher assistants to improve your student models if the gap of the teacher and the students big.
Cool.
Okay. Any question on this table? Yeah, you can watch it. I think it's beautiful. Okay, so in the last online meeting, I see some of you are really interested in the BERT models. I haven't watched these articles, but I found it online, so you can have a look into it. It's called the Distilling BERT models. It's basically, and you can compress the GAN model, GAN model, with the knowledge situation. I haven't watched it yet, but yeah, it's worth looking at. Any question, guys? I think it's the end of the meeting.
That's awesome. Okay, thanks, Patrick, for that excellent, really clear presentation. Thank you.
Right.
Yeah, I think we should maybe have a vote on what the next papers are to discuss. I think maybe application of distillation to BERT or applying BERT, I think would be interesting.
Yeah.
We can vote like what other things we want to learn.
Yeah, right.
Cool. Cool. Thank you. Like, does anyone else have any questions?
So this PowerPoint will be available or what?
Yeah.
Okay. Yeah. Thanks.
There'll be a record of this and the PowerPoint slides.
Okay. Thank you.
Cool. All right. Thank you. Thanks, Patrick.
Yeah. Thanks.
All right. Have a good weekend, guys.
Yeah.
Hey,
Have a good
bye.
weekend.
So we join the channel on Slack or Facebook group if you want to have a follow-up questions or if you want to continue or raise any topics for discussion. I left the links on all the direct messages that I gave you guys. So join in. Okay, have a good weekend.
Great.
Yeah.
Thank you.
Bye-bye, everyone.
Bye.